Hope you are able to see the slide.
Yes, sir.
Yes, sir, we can.
Are you able to see the slide? Okay. Yeah, okay. So before I take up the next topic, that is uh, on modeling broadband fading channels, just let me spend 5 minutes on the topic, whatever I have discussed in the previous class. Okay. Yeah. To begin with, uh, yes, so Suhas Reddy, can you just tell what are the key parameters we have discussed related to the channel?
1 minute, sir.
Yeah, I'm asking. I discussed in the previous class some of the key parameters. Okay, and I told their definition also. And if that parameter value is large, what happens? If that parameter value is small, what happens? And then how does it impacts on the LTE design? Okay, I think you can tell any one parameter.
Yes,
Of course, I
one
think
correct, sir. Button.
yeah, yeah, I discussed around 6 parameters, if I am correct.
So,
Okay.
like delay spread,
Ah,
and
yeah, you can tell about only
coherence.
delay spread.
So like if delay spread is larger, then intersymbol interference will be more, sir.
Okay, if the delay spread is larger than what?
Greater than relative spreads, like no, so like symbol time.
If the delay spread is greater than the symbol time, then I said it will be a frequency selective, right? Then I said, because see, you have to understand, if the delay spread is more than the symbol time, means what? So you will be keep receiving the uh, transmitted signal even after your symbol interval, right? So that leads to intersymbol interference. Hope I am clear.
Yes, sir.
Yeah, very good. So that is one parameter. Fine. Yeah, thank you. Similar to that, I think Madhura, can you tell another parameter?
Yes, sir.
Madhura. Yeah.
Coherence bandwidth, sir.
Yeah. What it is? Coherence bandwidth. Yes. Some.
Sir, it is a range of frequency over which a channel can be considered flat.
Okay. So coherence bandwidth is what? Is a range of frequencies over which the channel is considered flat, right?
Yes, sir.
And how this coherence bandwidth is related to delay spread?
It is inversely proportional, sir.
Very good. It is inversely proportional to the delay spread, right?
Yes,
So
sir.
I can say tau, right? So usually we represent delay spread by tau max or even tau RMS, that is RMS delay spread. So which is equal to 1 by BC, right? So if that is much less than the symbol time, then we say it is frequency flat, right? If it is greater than the symbol time, then we say it is a frequency selective. Yeah, what is its impact on LTE design? Yes, knowing the value of coherence bandwidth, you will be able to decide about what? Is any one of you? Coherence bandwidth. So I said we will be able to uh, fix the subcarrier width, right? Subcarrier width. Usually it will be 1/10 of the coherence bandwidth, I said. Okay. Yes, the next parameter is it possible to say from Mailaram? Mailaram.
So,
Yeah, can you say what is the next parameter?
So
So
Doppler
your
spread,
friends,
sir.
yeah, what it is? Can you just define what is Doppler spread? At least expression. How do we define that Doppler spread?
Bec- uh, Become non-negligible subcarrier orthogonality is compromised, sir.
No, that is fine. How do we define a Doppler spread? What is the expression for that Doppler spread? Yes, I said it depends on the relative speed of the transmitter and receiver, right? That is FD is equal to V. V is the what? That is the relative speed between the of the transmitter and receiver. Then the carrier frequency divided by the speed of light. Okay, so it is directly proportional to the carrier frequency and the speed of the transmitter and receiver at what rate they are traveling, right? Yeah, so that is the Doppler spread. Then what is the next parameter? Uh, yes, Meghana, can you say what is the next parameter? Meghana. Meghana. Meghana is not talking. Okay, what about Aman Sharma? Aman Sharma. Yes, Aman Sharma. If not there, then what about Dharma? Dharma.
Yes, sir.
Hmm. Yeah. Can you say what is the next parameter? So your friends have told three parameters. One is delay spread. Second one is coherence bandwidth. Third one is Doppler spread. So can you tell what is the next parameter I discussed today?
Angular spread, sir.
Angular spread. What it is? Can you just say what is angular spread?
One minute, sir.
1 minute. Okay, take one. Yes, in the meantime, what about others? Aman Sharma, just your messaging. Why you can't speak? Aman Sharma.
So yes, sir.
What, Meghana? Already train is gone. Hmm?
No, sir. The voice was delayed. That's why.
Yeah, but you have to sit at proper place. Network should be proper. Hmm? I ask you can say some of the parameters what I discussed.
Coherence
Your friends have to no, coherence.
time.
Coherence time. Yeah, can you tell what it is? Coherence time.
So it estimates the frequency channels.
It estimates the
Frequency channel.
no. What I said is if the coherence time is small, then it requires frequent channel estimation. Okay, so we need to do the frequent channel estimation that will limit the OFDM symbol duration. Okay, OFDM symbol duration.
Yes, sir.
But the advantage is it can provide greater time diversity, I said. And to relate that coherence time to the Doppler spread, so TC will be equal to 1 by FD, we say. TC. Okay, the coherence time is equal to 1 by FD. So they are inversely proportional, coherence time and Doppler spread. Okay, so and I gave a table in which for different bands of an LTE, okay, with a different speed of the vehicle, transmitter and receiver, right? And what will be the value of Doppler spread and coherence time, right? So I repeat once again, at 2.5 gigahertz, okay, if the vehicle is if the transmitter and receivers are moving at a speed of 350 kilometer per hour, I said the Doppler spread will be around 810 hertz. With that, the coherence time will be 1.2 milliseconds. So what it says is at high frequency, okay, and mobility. So frequency is also more and mobility is also more, okay. The channel will be changing up to 1000 times per second, what we can say. So if the coherence time is 1.2 millisecond, meaning that so the channel is going to change 1000 times per second. Just imagine if it is changing 1000 times per second, how do we know the uh, quality of the channel, right? So that is why these plays an important role, coherence time. Yes, Dharma, you said 1 minute. I think I took more than 1 minute. Is it possible to say what is angular spread? Dharma. Yes, what about Dharma? Yes, what about Akshata? Can you say what is angular spread?
Yes, sir.
Yeah. Yes, quickly. See, Dharma said 1 minute. I took 2 minutes to say something. Then you said yes. Then again, you're muting it. See, involvement is required. Okay, if you all involve and if you are able to try to understand the concepts, these are basic things. Okay, if these things are basics are clear, then you will be appreciating the technologies what we discuss in the further modules. Otherwise, you will keep quiet till the end of the semester because you are not knowing.
So the angular.
Uh,
Yes,
yeah,
sir.
tell me what is
Can I say,
uh,
sir?
yeah.
So the angular spread is nothing but the statistical distribution of the angle for the arriving energy.
Arriving energy. Okay, so statistical distribution of the
Angle of the arriving energy.
angle of the arriving energy. Okay, so what I said means when I was talking about the delay spread or even Doppler spread, coherence bandwidth or coherence time, there I was talking about the channel response, right, varies over time. Right, in a similar way, the channel can also vary over space. Okay, what you have said is exactly correct. Okay, so the thing is what we have to stress upon here is the channel can also vary over space. Means we need to understand the spatial temporal channels, right? So this angular spread that is, usually we express in terms of RMS. There is RMS angular spread of the channel, which we denote by theta RMS, right? So that is what it is an a statistical distribution of the angle of the arriving energy. Okay, uh, fine. After angular spread, yeah, what is its impact? The LTE design. Yes, by knowing the angular spread, what it is required. Okay, if it is more, what happens? If it is less, what happens? How it is related to another parameter? I think Chaitra can say.
Sir,
How
I
angular
was
spread? That is no. That is why I'm asking. No? Because today only you're coming. Only Saturday I'm finding out of 4 classes you're attending 1 class. It does not mean that you need not study. Na?
yes, sir. I'll look
Hmm.
into that.
You have to study and come. Otherwise, what today whatever I teach that may not go right.
Yes, sir.
Hmm. Yes. What about Siri? Siri. ನೋಡಿ ನಿಮ್ಮನ್ನು ಮಾತಾಡ್ಸೋದು ಅನ್ಮ್ಯೂಟ್ ಮಾಡಿ ಮಾತಾಡ್ಸೋದೇ ಗ್ರೇಟ್ ಚಾಲೆಂಜ್. ಹ್ಮ್ 4 ಸರ್ತಿ ಕರಿಬೇಕು, ಅವಾಗ ಆಮೇಲೆ ಹಲೋ ಸರ್ ಅಂತೀರ. So Siri don't want to talk. So that is not the reason. You have to update and come. Class ಇರ್ಲಿಲ್ಲ. Yes, what about Sai Lakshmi?
Sir.
Sai Lakshmi. Can you say how this angular spread is related? What is its impact on LTE design?
When the angular spread increases, the coherence distance decreases, or vice
Very good,
versa.
very good. Yeah, vice versa. Fine. So you mean to say is the coherence distance and the angular spread are inversely proportional. Very good.
Inversely
So as the
proportional.
angular spread increases, the coherence distance decreases, right? And vice versa. Fine.
Yes, sir.
Okay. So this coherence distance, is it possible to say the formula? How the coherence distance?
DC is
yeah, of course,
equal
DC is nothing but coherence
to
distance.
to lambda
That is
by
0.2, not 2. It is 0.2.
lambda.
Okay, 0.2 into lambda by theta
Yes,
RMS,
sir.
where theta RMS
Theta
is the
RMS.
RMS angular spread.
Yes,
Okay,
sir.
so basically this coherence distance will be determining the antenna spacings. Okay, actually it is angular spread and coherence distance are very very important in case of multiple antenna techniques. Okay, because we will be
Yes,
using
sir.
more than one antennas, right? So what will be the spacing between each antenna? Okay, so based on the value of this coherence distance, we can keep the or we can place the antennas at proper distance. Okay, with
Yes,
that
sir.
we will be able to achieve the desired goal, that is either what I wanted to say is if the coherence distance is very small, means antenna arrays can be effectively employed to provide the rich diversity, right? So
Yes,
we'll
sir.
discuss in detail about these things in the upcoming classes. Okay, so with this basic understanding and revision of these parameters, let me take up the next topic, that is about the modeling broadband fading channels. Okay. Yeah. Hope you are able to see the slide, right? Yeah.
Yes.
So this modeling, is able to see the slide. Yeah. So modeling of the broadband fading channels. Okay. So what I want to say here is if at all I want to set a benchmark and to design the wireless communication system, so development of the channel models is a very important task, because with that, by knowing the channel models, because it will be incorporating the variations in time, frequency, and space. So these three things are important: how the channel behaves with respect to variation in time, with respect to variation in frequency, and with respect to variation in space. Okay. Okay. So there are basically two major classes, okay, for modeling the broadband fading channels. One is the statistical channel model, and another one is the empirical channel models. Okay. So these statistical channel models are simple or simpler in nature, means it is very in implementation wise and other things are it is simple, and it is not considering any of the propagation environments. Okay, statistical channel models, and these statistical channel models are useful for analysis and simulations. Hope I am clear. I said there are two major classes of models. One is the statistical channel models. Second one is the empirical channel models. The statistical channel models are simpler and useful for analysis and simulations. Okay, and these statistical channel models will not be uh, considering any of the propagation environment. Okay, I will come to what are the propagation environment. I already discussed about reflection, right? Diffraction, scattering, shadow, path loss, all those things. So that all depends on, as I said, about the terrestrial environment also, right? Because the wireless channel is not a free space, because so many obstructions will be there. So these statistical channel models will not be considering the propagation environment. So it is useful for analysis and simulations, I said. With that, so we discuss these three different types of statistical channel models. One is Rayleigh fading, okay, which is usually used for non-line of sight paths. And second one is the Ricean distribution. So here, in case of Ricean distribution, it will be considering the line of sight channel. Okay, LOS channel means line of sight channel. That is the dominant path between the transmitter and receiver. So when we want to discuss about the line of sight path, then we go for Ricean distribution. Then the third one is the Nakagami-m fading. Okay, so third one is the Nakagami-m fading. So these are the three different statistical channel models which we are going to discuss. Then the second one, I said the empirical channel model, right? So this empirical channel model are slightly complicated, but these models will be representing the specific type of channel more accurately. Okay, means this is the empirical channel models are basically done by the field test. Okay, by doing experimentation, they will come to conclusion that okay, these are the different values. They consider the parameters, and they will tell about the path loss and other things. So one example of that model is the Hata model. So okay, fine. Okay, so to understand these models, okay, channel models, so there is a pedagogy for that, for developing these statistical channels. That pedagogy here I've given. So first, what we do is we consider. Already I told about the autocorrelation function. How does it useful in channel characteristics, right? Characterizing the channel. So what we do is first we consider the single channel with the sample corresponding to the single principal path between the transmitter and the receiver. Means, so this is for only one path. Okay, that is why I wrote the impulse response of the channel as h of tau comma t. Okay, you know what is tau and what is t. This is the delay and this is the time. So that channel impulse response I can write as s naught into del of tau comma t. So here what we are going to do is we are trying to quantify the value of h naught. Okay, how this the value of h naught, that is the channel gain, is distributed statistically. That is the first task. The second thing is, next we consider the channel sample h naught that changes over time. Okay, so here h of tau comma t is equal to h naught into h naught of t into del of tau. Okay, here it is only h naught. Here h naught of t means it is time varying, what I am considering here. So here what what we are doing is we are trying to quantify how does the value of h naught of t change over time. Okay, so how h naught of t is correlated with the h naught of t plus delta t, where delta t is a change in time. And the third step is we are going to consider for multiple dimensions, means both time and as well as delay considering. So I will come back to that. Okay, so let me start with the first thing, that is considering single channel and a single path. And as I said, this means when the signal received at the receiver, right, from multiple paths, depending upon the phase difference, right, the received signal may be a constructive one or it may be a destructive one. Hope you all remember this point. Yes, I discussed this point in the last class, where the signal received at the receiver, right, it will be received multiple times, right, from different paths, and they differ in phase. Okay, one signal maybe start with some phase and another signal may start with another phase. If their phase difference is large, okay, then I said the signal will be constructive. If the phase difference is small, then the received signal will be destructive. Means constructive means we will be receiving a signal amplitude much larger, okay, than the actual one. And if it destructive means the received signal amplitude will be smaller than the actual one. Okay, so keeping that in mind, so let us try to understand what is Rayleigh fading. Okay, hope you are able to see this Rayleigh fading.
Yes, sir.
Yeah. Yeah, then I told about the local scattering also, the concept of local scattering, right? I said two paths, two multiple paths I considered. Then at the receiver side, because of what? If the signals are received at the receiver side, which are close in time, right? So that is due to the local scattering I said, right? So if the number of scatterers is large and the angles of arrival between them are uncorrelated, then what I wanted to say is, I hope you're all aware of the central limit theorem, CLT. In mathematics, you might have studied. Okay, from the central limit theorem, it is shown that the in phase and quadrature components of the received signal. Okay, R of t is the envelope of the signal, we say, right? So due to the central limit theorem, we can say that the in phase and quadrature components of the envelope of the signal, which are denoted as what? In phase we write Ri of t, and quadrature signal we write Rq of t. Okay, of course I might have used different notations in the previous semester. I used to write S of t as a received signal and transmitted signal, right? Then Si of t and Sq of t. So here we are using R of t, then Ri of t and Rq of t are the what? In phase and quadrature components of the two independent time correlated Gaussian random process, what we can say. I said no, the received envelope signal, right, R of t at time t equal to 0. So just I'm saying what is R of 0, which will be equal to Ri of 0 plus Rq of 0, right? So this Ri of 0 and Rq of 0 are the Gaussian random variables. Okay, and we can say that the distribution of this envelope, that is this amplitude, right, R of t, will be what? So this is a Cartesian form, right? So I can write amplitude as what? Square root of R square I plus R square Q, and this we say it is a Rayleigh. Okay, so the distribution of the envelope amplitude will be Rayleigh. Hope this point is clear. These are all known facts only, maybe with different notations we are saying, that's all. Okay, yes, the distribution of the envelope of the signal means its amplitude can be written as R magnitude, right, which is equal to square root of R square I plus R square Q, which is Rayleigh. This is the magnitude. Okay, that is amplitude, what I can say. And the received power will be what? R square. Okay, R mod square, right? So which is equal to R square I plus R square Q, and the power will be exponentially distributed. Okay, two things are there here. One is the amplitude, second one is the power. So amplitude distribution is Rayleigh and power distribution is exponential. Okay, hope I I am conveying what I wanted to convey. So what I wanted to say about Rayleigh fading is, if the number of scatterers is large and the angles of arrival between them are uncorrelated, as per the central limit theorem, what we can say is the in phase and quadrature components will be following two independent time correlated Gaussian random process. Okay, so here I have taken the snapshot of the R of t at a time t equal to 0. I can say R of 0 is equal to Ri of 0 plus Rq of 0. So Ri of 0 and Rq of 0 are the what? In phase and quadrature components, right? And they are Gaussian random variables. And the distribution of these Gaussian random variables that is with respect to amplitude is this, that is square root of r square a plus r square q, which is Rayleigh, we say. And the received power, which we denote as r mod square, which is equal to r square a plus r square q, and that distribution is exponential. Okay, then how do we express that mathematically? So these are the expressions for expressing in the statistical way, that is the Rayleigh fading, what we say. So this is the amplitude, okay, amplitude distribution, which is equal to, usually we say f r mod of x is equal to 2x by pr. So where p suffix r is the average received power, okay, d power minus x square by pr. So this is the Rayleigh distribution, what we say. Okay, so amplitude is Rayleigh distributed, and power, so the second equation is the power. Okay, f r mod square of x is equal to 1 by pr into e power minus x by pr, and this, what I said, it is a exponentially distributed. So power is exponentially distributed, amplitude is Rayleigh distributed. Hope you are aware of these distributions. Gaussian distribution you are aware, right? You have said so much. Similar to that, it is another Rayleigh. Yes, is this equation is clear? Amplitude and power. Amplitude is Rayleigh distributed and power is exponentially distributed. Okay. And okay, as I said, no, this Ri and Rq are the what? In phase and quadrature components, right? And they are the Gaussian random variables, right? So with zero mean and variance will be equal to PR by 2. As said, PR is the average received power, right? So the variance value is that much. And I can write phase of that envelope, okay, as theta r is equal to tan inverse of RQ by RI. This you all know, right? How to express magnitude and how to express angle. So, well, basic things which you are aware. And we say this is uniformly distributed over the interval 0 to 2 pi. Okay, so this is about the distribution, and just let me say about this diagram. So which is basically tells about the three major channel attenuation factors, right? So one, as I said, path loss, right? So path loss is, we thought it is due to distance, right? So the dotted line is the path loss, right? Dotted line is the path loss, and which is basically, I said, we consider that as a average, okay, or expected value, right? Expectation value, right? Path loss is average value we consider. Then from that average value, due to shadowing, there will be variations in the received signal. So that is shown with this one, okay, this line. So that is what shadowing plus path loss I am writing. Then I am showing another one, that is if random fluctuations, right? So that is due to fading, what we say. Okay, I hope you are able to understand the difference between path loss, shadowing, and fading. Okay, so path loss, we consider it is an average value, right? Then shadowing, we say variation from that average value, variation in the received signal strength from that value. right? Then fading is what? From that mean value, there will be a random fluctuations. Fluctuations in the received signal is known as a fading, what I can say. Hope this point is clear, this picture. It is conveying three things. Yes, my dear students, is it clear? I am asking. Fading is nothing but the random fluctuations in the received signal. Okay. What is path loss? It is a loss in the received signal due to distance between the transmitter and the receiver. What is shadowing? Shadowing is also a loss in the received signal due to the objects between the transmitter and the receiver. Okay. I said it may means the signal may go through walls of the building, or it may go through the trees, right, or it may go through the hills and other things. Due to that, there will be attenuation in the received signal, that we call it as a shadowing. Hope this picture is clear. So this picture is what? Received power, which is we say in dBm versus the distance. Will you be able to write this diagram if we say how path loss, shadowing and fading is shown? Hope this point is clear. Fading is what? Yes, what is fading? I said. Yes, my dear students, I think nobody is responding and I keep talking. Fading. Looking at that diagram, you are not able to say what is fading. Yes, Anup. Anup. You unmute, man. Anup. Not talking also. No response. I don't know. Simply long. Yes, what about Gautam? Gautam. Yes, Pranav.
Yes, sir.
Yeah, I shown the diagram. Could you observe that what it is? Still it is visible. I have not removed that.
So, like, it shows the major channel attenuation factors, sir.
Major channel attenuation factors, right? One is path loss, I said. So that is what? Path loss is what? I said it is an average value, right? Then
Yes, sir.
shadowing, from that average, there will be a variation in the signal strength. Then fading is what? The random fluctuations, okay, around this path loss and shadowing, right? So there will be fluctuations in the received signal, that we call it as a fading. Just I'm showing that, but people are not responding. See, to look this diagram, it may be more complicated. If you understand, it becomes very simple, very easy to write also. Okay, so without putting your mind, you may feel that, oh, something which we cannot. Nothing like that. But when people are not responding, what to understand? Hmm? See that Anup I am asking is neither unmuting nor talking. Neither muting nor talking. Hmm? Okay, so Rayleigh fading I discussed. Okay, Rayleigh fading is what? How do we express that? So these are the two equations which are important. What I can say. How do I say the received signal amplitude is distributed? Right. The received signal amplitude is distributed as a Rayleigh. How I express that? I express that distribution as f suffix r mod of x, right? F suffix mod of r of x is equal to 2x by pr in d power minus x square by pr. So this is a Rayleigh distribution. Okay, where the value of x will be greater than equal to 0. and the received power. Okay, power will be what? R mod of square, right? So I said power will be distributed exponentially. That is why that exponential distribution will be written like this. That is 1 by PR into e power minus x by PR. So these two equations, if you are able to understand and say yes, how it is Rayleigh and how it is exponential, means how amplitude is distributed as a Rayleigh and how power is distributed as exponentially. So looking at the expression, we can say it is exponentially distributed, and this is Rayleigh. Okay, so minus x square by PR is, we say it is Rayleigh, and e power minus x by PR is a exponential distribution. Okay, so power is distributed exponentially, and amplitude is distributed as Rayleigh, we say. Okay, so with this small discussion about Rayleigh fading, so let me just go to the next one. So that is Ricean distribution. Okay, so what is Ricean distribution? As I said, we use Ricean distribution for the line of sight channels. Okay, means we use the Ricean distribution to say about amplitude and power distribution. Okay, when there is a dominant path, so the dominant path will be due to line of sight path only. Okay, and we can express the Ricean distribution as like this. So f r magnitude is nothing but amplitude, right? Distribution is x by sigma square into e power minus of x square plus mu square divided by 2 sigma square I naught dx mu by sigma square. Okay, of course, this equation seems to be complicated, but it is very simple to understand. So what is this mu square? Mu square is the power of the line of sight path component. Okay, mu square is what? Is the power of the line of sight component. And what is I naught? I naught is the zeroth order modified Bessel function of the first kind. Okay, okay, and it can be generalized. Okay, uh, means with respect to the Rayleigh distribution by making mu equal to 0. Okay, if I make mu equal to 0, then this I naught into x mu by sigma square becomes 1. So with that, this Ricean distribution simplifies to, or reduces to, what I can say as a Rayleigh distribution. Okay, so as I said, the Ricean distribution depends on line of sight path component, right? So that line of sight path component power mu square, which we use as a means which is used to characterize the channel, okay, by the relative strength of the line of sight and scattered paths. So which is divided by the factor k, so which is equal to mu square divided by 2 sigma square. Okay, so I think I will not make that much complicated. What you need to understand is Rayleigh fading is used for scattering type of environment, and Ricean distribution is used for line of sight paths. I think these two things you can keep in mind, but expression you have to answer because it is standard equation. Okay. Then the third one, that is I said about Nakagami-m fading, right? So it is a general model, what I can say. So here the distribution function, okay, means how the amplitude is distributed with respect to this Nakagami is this. What I can say, f, that is the probability density function, right? This f mod of r of x is equal to 2 into m power m x power 2 m minus 1 by this one. Okay, this is for magnitude and this is for power. Okay, the power distribution for Nakagami fading is this, m by pr to the power of m. So here everything is to the power of m. So where, what is that m? So when m is equal to 1, what we can say is it is, so here what is m is defined, okay, it is k plus 1 of whole square divided by 2k plus 1, and what is k I said in the previous case, right? How do we define that k? K is mu square divided by 2 sigma square. So with that, when m is equal to 1, we say it is a Ricean distribution in this equation only. if I substitute m as 1, and as the value of m tends to infinity, then the received power tends to become constant. Then the power distribution for the Nakagami fading is this, right? So when the value of m is greater than or equal to 0.5, we say here. And just to understand with respect to the plot, yeah. So this is the plot which shows all the three statistical models. Okay. So this is the probability distribution of those three statistical models. One is the Rayleigh. Okay, the thick line is the Rayleigh distribution, right? I was talking in Rayleigh as what Ri of t and Rq of t are Gaussian random variables, right? So hope you are aware how the Gaussian pulse will be. Then the Ricean distribution, so with k is equal to 1 is this one, okay, and this one is the Nakagami, okay, that is for m is equal to 2, it is shown here. So I think this will be resembling the Gaussian pulse, right? Yes, are you aware what is the Gaussian pulse? How does it looks? Hmm? I think I will skip this. There is no point when I'm not getting response. Okay, just I will say how. So this is about the autocorrelation of the signal. Means I was talking about statistical correlation. Okay, how the received signal will be correlated in time and as well as correlated in frequency. So two things we need to understand. I don't know to what extent you will be able to grasp this. I think I will skip this. I will stop with this, I feel. Okay. Otherwise, I thought you will be able to respond and able to grasp, but no grasping power. So there is no point in discussing much about these things. Okay. Okay. What I will do is I will do one thing because I don't know to what extent you are able to grasp these concepts. These are little bit statistical. This one in the module 1, the first part is completely done. The second part, so few more things are there which I need to say. Otherwise, you will not be following the rest of the modules. So I will be talking two more things. One is about narrow band fading mitigation techniques, and another one is wideband fading mitigation techniques. Okay, so you will be studying those things in further upcoming slides or upcoming lectures. Okay, just I will say uh, about these two things. Okay, I think looking at this picture, you are able to say something. Is this picture is clear? Yes, able to see this diagram. Somewhere I have shown this type of diagram. FC, then FC plus FD, then FC minus FD, right? This is due to what? This is due to Doppler spread, I said, right? So when I transmit a single impulse, okay, maybe a single tone sinusoidal signal at frequency FC, due to the Doppler spread, okay, due to the relative motion of transmitter and receiver, at the receiver, I will be receiving the signal other than FC. Okay, not only at FC, I will be receiving a signal in a range that is from FC minus FD to FC plus FD. Okay, so this is the Doppler's power spectrum, what I can say. Okay, Doppler power spectrum. So that will be telling or determining the correlation envelope of the channel. In means this is in frequency domain. How does it looks in time domain? Okay, so this is in time domain, what I can say. So here it is written, see, Rayleigh distribution. How does it varies? Okay. So this is your coherence time, which is equal to 1 by FD. So over that time, how does the channel behaves? Okay. Another thing is, it is about the what? The second thing is for the multipath intensity profile. It means here what happens as time increases, now it is decreasing, right? That is RMS delay spread. It is okay. RMS delay spread is also decreasing as delay increases, right? As it is. So how does it look in frequency domain? Okay, here we are relating with respect to the coherence bandwidth, because coherence bandwidth and delay spread are related, right? So coherence bandwidth will be inverse of delay spread. So usually we say it is 5 times the delay spread. So that is why it is written BC is equal to 1 by 5 times the RMS delay spread. So this is one aspect. Then another thing is, yeah, this is about the time dispersive nature of the channel. Okay, what is the time dispersive nature? Time dispersive and as well as selective. What I can say, two things are there. The first one is the dispersive in time. Okay, if the signal dispersive or dispersion means what? Spreading of the signal. Okay, so it is dispersed or spreaded in time, right? So when it is spreaded in time, in frequency it will be a selective. Okay, so when the signal is spreaded in time, it will be selective in frequency. Similarly, if the signal is selective in time, then it will be dispersive in frequency. So just to understand between time domain and frequency domain. In case of time domain, if it is dispersive, in case it will be selective in case of frequency domain. Okay, and if it is selective in time domain, and it will be dispersive in frequency domain. So these things are really useful for you people to know the impact of these things. Okay, if the signal is dispersive in time and it will be selective in frequency, so what is its advantage? Okay, or if it is selective in time and it is going to be dispersive in frequency, what is its impact on other parameters of the channel? Okay, so the dispersion selectivity, both are duality. What I can say, if it is dispersive in time, I can say it will be selective in frequency, right? And if it is selective in time, it will be dispersive in frequency. Okay. Yes, I think with this, let me stop this.